Well, see, now it got worse because now you're trying to match outfits. All right, shut up! We can have a second quiz.
Okay, let's do it.
I will stab you.
All right, so see, I just did this. I just deleted everything. It's awesome. I love that. All that gold. Hopefully we don't need one of those things we had on there. We'll just write it again. All right, so the quiz was define, what did I say, call it sum? So this guy's going to be a lambda. It's going to take a list as a parameter. So if this list is null, so if we're out of crap to return, we can just boil down to 0, right? Otherwise, what do? We add the car of the list to sum of cooter of the list. Make sense? So how many people got it right? So Pebbles, how wrong did you get it? I'm going to look. Yeah, see, Levi's isn't horrible. Levi, like, you could tell that he pretty much knew what he was doing, just kind of things went south. Usually there's money inside yours. To be honest, it's better than I expected. I mean, this is worth some points. Congratulations. All right. So homework. What was the homework assignment? Which numbers? To what?
6. To 3.
All right. All right, so 1.26 to 1.3. Did I give you a shorter one?
That's this one.
Nope, that's the next one.
Oh, the next one's a shorter one, right?
Yeah, it's
All right.
not really.
Define shorter.
Problems. It's not actually short at all. Yeah, there's just a lot of text. You have
There's 2 1 stars in there though.
Yeah, but I think you might have the ratings wrong. I think 1 stars are harder than 2 stars.
I don't think so.
I don't know. If you look at the 3 star, the 3 star is definitely not easier than 1 star.
They're definitely not easier, is what you said? All right.
Where's the 3 star?
All right, so we already did 1.25?
Yes.
Okay, so we're on 1.26. So up. All right, up list removes a pair of parentheses from each top level element of the list. If a top level element is not a list, it is included in the result as is. All right, so we're going to go through our list each time through. We want to find out if it's a list or not. If it's not, we're going to cons it on. If it is, we need to do something to it, right? Okay, and what do we do to it? We need to remove a set of parentheses. How do we remove a set of parentheses? Sending the contents to...
You want to get rid of a set of parentheses.
Oh, okay.
You take
Go through it.
Set of parentheses and stick it in a
Yep. So go through the list in its entirety, consing each element onto a brand new list, which should take out the outer list. So, for instance, if we have a situation like this, that guy right there, what do we do with that to get the list this? We're going to use append. That's what you pointed out, right? Okay. So if it's a normal element, we cons it. If it's a list, we append. Sound like a fair statement? All right. So define up to be a lambda expression that takes in a list as a parameter. Well, the first thing it's going to do is it's going to ask if our list is null. If our list...
You probably need to ask that question.
Well...
Can you just straight up say no? That'd be fun.
What? If null, LST, you almost will be able to when we start doing cons. I haven't introduced cons to you yet. Huh?
Cons?
Cond.
Oh.
C-O-N-D.
Well, you
It's
mentioned it in
like-
the
Oh,
lecture,
position.
and I think even
Okay.
on a-
Yeah, whatever.
but yeah, we didn't actually-
So if the list is null, then we're going to return the empty list because we kind of know that we're going to be kind of building lists. So our endpoint's going to be so we're kind of following the same structures we've had up to this point. Okay. Otherwise, we know that there's a car to the list. We need to find out what kind of animal the car is. So we'll ask if list car LST. So if we're dealing with a list, then what do we do with it? We append the car of LST onto up of the cooter of LST. If it's not a list, then we cons the car of LST onto up of the cooter of LST. That. Let's test this.
Oh,
He told you he was biding his time.
Well, he's still here. You gotta
All right, so there's our list 1, 2, 3, 4. It's slow acting. What happens first is you drown on the inside. Then your eyes start swelling. Actually, that would be the worst if your eyes popped and then you started dying. That was the wrong order. See, I'm okay with this because I just came from Bible study, so I'm covered. All right, so is this the right output? Oh, yeah, I mean, so like I put on, for those of you who missed it, I put on Slack, Tuesdays starting today, from noon to 1, was the faculty, student, staff, Bible study, Daily Flippy comes with free lunch. That's why it was times 20.
Ah,
Free lunch.
times equals 20.
I'm basically buying you lunch. Well, I'm not buying you lunch, but I'm going to be there so you can pretend like I'm buying you lunch. All right, every Tuesday, noon to 1.
Really market that John the Baptist bobblehead.
John the Baptist bobblehead. Some assembly required.
That's terrible.
You guys have heard that before, right? It's from that Harry Carey calls the first baseball game. Just like, go with the host with the Mo's. Go with Nabisco. It's not like those cheap brand sacraments. Stick to the roof of your mouth. If you haven't, look it up on YouTube sometime. It's hilarious. He hit a bases empty grand slam. We haven't seen a miracle like that since Fishes and Loaves night. I'm just like racking up Christian worldview here. All right. So does this look good for the first question? Up. Any questions on that one? So this is drilling that difference between append and cons and how it works. So append glues two lists together. Okay, so like almost like concatenation, right? Where cons builds up a brand new list. All right, so let's see. Next one, flatten. That was a 2-star? Up. Okay. Flatten returns a list of the symbols contained in S-list in the order in which they occur when S-list is printed. Intuitively, flatten removes all the inner parentheses from its argument. So flatten ABC okay, so it extracts all the elements, all the non-list stuff, right? Is that what it does?
Yeah.
Okay. So we're going to go through, so this is going to be a function that takes in a list, just like any other list. We're going to be building a new list, so we're probably going to do that same structure that if the list is null, return the empty list, otherwise do something, right? So let's start with that structure, and then we'll figure out what we're going to do. So we'll define flatten to be a lambda expression that takes in a, actually what is it so called, an S list, just for to match what it has there. Then we'll say if null S list, return the empty list. Otherwise, we need to do our logic. Okay? Now, if the car of S list is a normal thing, that is, if it's a symbol in this case, we just want to cons it. Correct? We don't need to do anything special if it's a normal thing. So, if symbol car S list, then we'll cons car of S list onto whatever's returned by flatten passing it the cooter of S list. So that's our easy case, right? If we look at the very first element, it's already a normal symbol, not inside of a list or anything like that. We're just going to grab it. Actually, does this, just real quick, just so I see this. This guy only, yeah, it returns a list of symbols. So guaranteed that it contains symbols or lists of symbols. So I don't have to worry about numbers here. All right. So if I'm looking at a plain Jane symbol, I'll just cons it onto my running total. Otherwise, what do I need to do? I need to build a new list, right? And I always come up with symbols eventually. So will I cons flatten on the car of S list onto whatever's returned by flatten on the cooter of S list? Will that do it? If it's just a normal dude, I'll just go ahead and grab the first element and cons it onto a running total. Otherwise, I'm going to have to call flatten on the first part. What kind of animal does flatten give me? When flatten is done, it builds a list, correct? What happens if I cons a list onto a list? So if I cons the list 1, 2 onto the list 2, 3, what do I get? The list containing two lists, right? Is that what I want here? What do I want here? I want the list 1, 2 and the list 2, 3, or whatever I said, to ultimately be the list 1, 2, 2, 3. What does it take to do that? Append. So again, this is a drill between consing and appending. So we're going to append the result of calling flatten the first time to the result of calling flatten the second time. Each of those will ultimately end up being lists in and of themselves. And then we'll just glue them together. We know that they're going to be lists containing only symbols because that's what we do right here in this production. This is our representation of a production from our grammar. That make sense? So let's test this dude. We'll do it on our simple case first. Make sure that doesn't get destroyed. Okay, so that gives us what we expected. That gives us what we expected. This one looks mean. That gives us what we expected. All right. So that look good? All right, so that was up and flatten. All right, questions on that one? Now, just to give a kind of a poll for the class, in doing the homework, those first two, how did those feel in terms of difficulty when you were doing them for your homework assignment? Difficult, easy, about right? So about right kind of felt challenging, but not overly challenging. So those first two weren't bad. Did anybody find the first two terrifying? Did you actually try to do it?
Yeah.
Oh, well, that's good. Well, I'm proud of you that you tried. It's an improvement, step in the right direction. Did you ask for help?
Google.
You have classmates.
Yeah, worry.
Yeah, you'd rather just get zeros. That makes sense. Real logical. Haxton has even agreed to help people. He's rough around the edges, but he's bright. He has fun with these assignments. It's probably the only class that's challenging him, right? What are we actually looking at on our laptop here?
The next don't work.
Huh?
The next don't work.
The who?
The next homework.
Oh, you're doing the next homework already. Okay, I got it. Because this one's boring you.
You already did it.
Well, hopefully all of you already did it. Because I can see when it's late in the grading thing. All right. So 1.28, ugh. This one looks terrifying. All right. So merge. LOI, what does that stand for? List of integers. Okay, so we have two lists of integers where, there it says right there. Should just kept reading. Two lists of integers that are sorted in ascending order. Returns a sorted list of all the integers from the list of integers 1 and the list of integers 2. What step does this sound like? And from what? Remember merge sort? After we make all those recursive calls, we have two partially sorted lists, and we merge them together. Isn't that what this is? I'm getting blank stares. Abe, isn't that what this is? Do you recognize that? Do you see the pattern? Remember merge sort? Remember we learned merge sort in another class, not this class.
Yeah.
When we just kept dividing up our lists until we had one list, because by definition a one list is sorted. And then we would bounce back up, and then we would do that merge step where we had two sublists that were each sorted in and of themselves. And we needed to produce a single list that was sorted across both of them. That was the merge step. So that's what we're doing here. And that's why it's called merge. Get it? So we made that connection now. Anybody make the connection when they were doing their homework? Pebbles?
Kind of.
I don't know, right?
Well, no, I just wanted to know if you made the connection. That's not a getting it right or wrong thing.
I did it, and I was like, I'm not even gonna bother.
You need to are you paying attention to what I'm saying in real time here? I just used it. I just connected what we're doing in here to a previous course.
Oh yeah, I did it.
I hope he's kidding. All right. We're going to stop that conversation. It was two separate conversations. They nothing to do with each other. All right, so we have two separate lists. We need to walk through both lists until both of them are empty, right? So if we think about that merge step when we wrote for merge sort, we would remember. I can duplicate what we talked about. I would say, which should come first, this element or this element? Which should come first, an illegal position or this element? This element always beats an illegal position, right? Okay, so we need to walk through until we've emptied out everything from both lists, always taking the greater of the cars. But make sure you don't take the cars of an empty list. Make sense? Abe, does that make sense?
Yep.
Did you get this one?
Maybe this one.
Oh, was this one shouldn't be that bad, was it?
It was harder than the first two, but.
Well, it should be harder than the first two. The first two, I could have a trained monkey do those.
Where can I get said monkey?
I'm just giving. Nah, this one's probably more mentally challenging than the first two by a lot. Okay, so let's get rid of that. Define merge to be a lambda that takes a LOI1 and an LOI2. Is that what it was? Okay. So we need to keep going as long as they both have elements in them. Okay. As soon as at least one of them doesn't have elements in them, I can append. Correct? Okay, so we're going to start off by saying we're going to write the hard part of this first. The hard part's going to be as long as they both have stuff in them, let's compare the cars and pick the winner. Okay, so let's start with that. So we're going to say if, I'm going to start writing it for one of them, we're going to say null LOI1 and null LOI2 if we have two empty lists. We're kind of building a final list here, right? So what's my end case when I am building a list and I'm out of stuff to do? Somebody who hasn't really answered stuff today. When I'm building a list and I've run out of things to do, what's my end case? Empty list, right? So I'll return the empty list. Now, if I'm still kicking, I know at least one of my lists has stuff in it, right? Okay, so now I need to ask that. We have different ways we can pull this off. How do we ask if both lists have stuff in them? We know that they're both not empty at this point. But now I want to ask if one of them is empty. If null LOI1, so if the first list is empty, then what will I do? Return LOI2.
Do you even need the first step?
Well, sort of. We'll get there.
Once you're doing it weird way, you gotta get rid of the.
Remember what I'm trying to do. I'm trying to form a structure that you guys can rely on every single time you write programs. There's going to be more optimal ways of doing this, and we'll fix it. Okay, so we're thinking about the logic here. If we were writing this in Java, we're only going to do stuff if there's stuff in our lists, right? All right. So when there's nothing in both lists, we'll return the empty list. That'll be the end of our calls. That's consistent with what we've been doing up to this point, right? So as you guys approach this problem, I would have expected you to go down this rabbit hole first. All right? So now, if I'm still kicking, I know that there must be something in at least one of my lists. Okay? So, if my first list is empty, just back up here real quick, then I'm going to return my second list. Otherwise, if my second list is empty, I'm going to return my first list. Else. At this point in time, if I'm here, I know that both lists have things in them. So now I need to ask which one should come first. If greater than car LOI1, car LOI2. So if the first list has a bigger value in the first element than the second list, then I'm going to cons the car of LOI1 onto whatever's returned by calling merge on the cooter of LOI1, passing it LOI2. Otherwise, I'll cons the car of LOI2 onto calling merge on LOI1 and the cooter of LOI2. Make sense? So following that structure, that's kind of the rabbit hole we would have gone down off the patterns we've done in our other homework assignments. Okay, we just kept reducing how things could be. If they're both empty, that means we're done. What do we do when we're done and we're building lists? You return the empty list. Otherwise, if the first one is empty, return the second one. Otherwise, if the second one is empty, return the first one. Otherwise, and we're going to see our problem here. Otherwise, if the car of the first one is greater than the car of the second one, we're going to cons the car of the first one onto whatever merge returns for the rest. Taking the rest of the first list and leaving the second list alone because we haven't removed a value from it. Otherwise, we're going to cons the car of the second list, because that's the winner, onto merge, passing it the first list as is, and the rest of the second list. What's wrong with using cons here? What kind of animal does merge return? Well, when you look at it here, what kind of animal is that? Cat, dog, or list? It's a list. What kind of animal is this? Cat, dog, or list? Okay, that was the list. So, when I cons something onto a list, what do I get?
A list where the first element is a list.
Is this guy a list?
No.
What's that guy? It's an element. So if I cons the value 5 onto the list 1, 2, what will I get? The list 5, 1, 2. Is that what I want?
Get rid of that first if it works.
Let's roll with it here.
Actually, never mind. You're doing something weird. Actually, no.
Remember what we're drilling today is cons versus appends. When do we use each one? Okay. Let's see the result we get. So we'll go ahead and do our first merge here. So list 12814. That look right to you? Let's do our second call. That one look right to you? Okay, so let's walk through this first one, because the first one's obviously simpler, right? So I have two lists that are coming in, the list 1-4 and the list 1-2-8.
Why are you doing greater than? Shouldn't it be less than?
You do less than.
Oh, what's greater than, it'll do it backwards. So you want to see?
Yeah.
If you do it less.
Yeah, it would just do it in descending order, right?
No.
No.
No, I don't see it right.
Oh.
The two-
Yeah, you're right. You're right. So these are the right outputs, but I want to trace through this, and I want you to see where we can improve upon this first part. So we take in 1-4 and 1-2-8. This first thing allows us to ask the question, are they both empty? They're not. They're not both empty. At least one of them has something in it. Okay? If they were both empty, we would return the empty list here. So we're still kicking. Is the first list empty? No. Is the second list empty? No. I'm going to be introducing a con to you here is what I'm doing. All right, is the second list empty? No. So we know we have stuff to check. So if the first element of the first list is less than the first element of the second list, then we're going to cons that first element onto whatever merge boils down to. question here for what we're drilling today is the difference between cons and append. If I cons an element onto a list, I get a list containing whatever the second list was with the element as the first element. Make sense? That's what cons does. That's not wrong for what we want to do here. After doing the first two problems, it's easy to get lulled into thinking an append is better, right? We almost want to try to use append all over the place. Append is only when we have a list and another list and want to produce a single list containing all the elements of both. Okay? Because if I cons a list onto a list, I'll get a list whose first element will be that list and whose rest will be the second list. So understand how cons and append work and when we use each. One's not better than the other. We use them for different purposes. All right, so that's why this is a cons here, and that's why this is a cons here. Now, I'm going to rewrite this using cons, C-O-N-D, which is a way of helping our syntax for writing nested if statements. All right, so I'm going to write a second version of this. So we're going to define merge to be a lambda that takes out, here, let's call it merge 2. To be a lambda that takes an LOI 1 and an LOI 2, and we're going to start a cond. Okay, a cond equivalent in our modern programming languages is something we often ignore, and that's switch statements. Okay, so what I'm going to do here is I'm going to write my first Boolean expression. I'm going to steal this one up here. So that's my first one. Then I'm going to steal my second one. Oh, sorry. And then finally, so let's just change these all to merge 2, make sure we didn't break anything. Okay, so right off the bat, just at a glance, wouldn't you say that this looks a lot cleaner than this guy up here? Okay, so cons allow us to ask a series of Boolean expressions, series of questions. So a cond each, almost think about like production. So cons match up to grammars very well. It's kind of the purpose of them with why we use them in here. So a cond always has an opening and closing parenthesis. Inside of that opening and closing parenthesis, we have a Boolean expression and what to do if it's true. Make sense? That's the syntax for a cond. Open and closing parenthesis, whose first element, so it's a list, whose first element is a Boolean expression, and whose second element is what should you do if the Boolean expression is true. So this is that same representation using a cond. Okay, so now, how could we clean this up even further? Some people were saying that we don't even need that first line. What's a better way of writing this? Go ahead.
Because you don't need to return an empty list, because when you're basically, you can get rid of the first line by just basically you just get rid of the first line because you don't need to cons on the empty list. You can just append the rest of LOI2 or LOI1 depending which one runs out first.
Mm-hmm. Yep. So we don't need to end with an empty list because we know that we're eventually going to have a list as our second element. It'll either be LOI1 or LOI2. One of those two is going to still have stuff in it after the other guy runs out. Correct? So if we take this out entirely, that entire production, which is a lot easier to remove in a con, by the way. See, we get the exact same results. Now, the important thing to recognize there is it's not that we didn't need that first line. That first line, the purpose is based on our old structure. The old structure of all of our solutions up to this point is we always had to end our list building procedures with a list. Because of the nature of this specific problem, we're guaranteed to end the list building process with a list because at some point, we're going to either hit this production or this production. Make sense? Go ahead.
Don't you still need it in case there is nothing from the beginning? Or no?
So, for example, if we were calling merge 2 on 2 empty lists,
Yeah. Would just return nothing.
well, what it's going to do, it's going to return the empty list because it's going to check, is this one null first? And ultimately just boil down to this one. Make sense? So not required, but not wrong. And realistically, based on what I've been teaching in here, I would have expected a majority of your solutions to be closer to this than omitting that first line. Okay? If not your final solution, at least your first pass at the solution until you recognize, oh, I already have lists. But the important thing to notice there is the reason why our normal structure is to always return that empty list is because that's our finishing touch for either an append or a cons. We need a list in there, right? All right. So questions on merge. And now you could add cons to your toolbox. We can go do that real quick. They will start giving you some cleaner solutions, cleaner looking solutions that start looking more like grammars, which is going to be very good because now that we're getting pretty close to being able to understand scheme, unless you're Levi on Tuesdays. I forgot how to scheme. That's worth some points. That's just that statement. Now that we're getting close to that, we're going to start jumping into the language structure stuff where we're going to be dealing with grammars a lot. So having a syntax that is kind of compatible with how grammars look is going to be beneficial to us. Plus, it already cleans stuff up for us. All right, so that was merge. Sort returns a list of the elements of LOI in ascending order. Now, hopefully none of you used the built-in sort function. Wasn't in your toolbox. Wasn't in your toolbox. All right, so we're taking a list of numbers. We need to sort it.
It's not gonna let you name it sort.
Oh, because of the built-in sort function? Actually, just,
That's how we knew there was a sort function.
no.
We tried to name it sort.
Yeah.
Oh, it's already defined.
Yeah, so if you just do this,
Sorting. Probably wants a.
what's know whether or not it's ascending or descending, how you want to sort it. Unimportant for us. All right. Not not for using this function, because I'm not introducing that function yet.
Give it to the next problem.
Okay, so define sort 2, right? You can call it that. Sort x. Sort x. Let's call it sort x.
Called mine sort KK things.
Sort KK things.
Yep.
That kind of things.
That would be nice.
Okay, and this guy's going to take a list of integers as a parameter. All right, so I have a list of numbers. How do I sort them?
There's a function built into this for that.
Without having that function. So I'm taking it this one was the challenge. Okay.
The next one was pretty much this one. But
It was pretty much exactly the same, except you just substituted.
something up that less than sign.
Mhm. Okay, so how do we go about sorting a list of numbers? Forget about scheme for a second. How do we sort numbers when we first learned this stuff in Java?
You compare two numbers that are next to each other in the index and see if it's like one's greater or less than, and if it's, less than, you swap it.
Bubble sort.
Okay, so bubble sort is kind of usually our first one where we find something, we bump it up to the top of the list, right? Okay. Is that going to work here?
Ish.
Could make it work. What if we just kind of, what if we just, we're sitting out there in the wild, we have a list of integers, and I ask you what element should come first? Smallest. How do we find the smallest number?
Wasn't it the first on the list? Or was this one not? Okay, this one.
So let's just start with that. I want to have a function that takes a list of integers and finds the smallest number in that list of integers. How do I write that? So here, let's go back. Find smallest. Remember that thing from the book that says you should break problems down to their smallest parts? Okay, so just a list of integers. I want to find the smallest value in that list of integers. How would you do that?
Could use let.
Oh, let's would be excellent for this. Let's would be excellent for this. Okay. So how do you want to use that?
Yeah.
Take the car and compare it, see if the next one's less than, or take the car, and then you return the gooder or whatever, and then compare those, the car, the gooder, and the car, the first one is let. So you store the car into the let.
Actually, let me ask you this real quick. Do we know how to set a variable yet?
Yeah.
We know how to use let kind of.
Well, right. But did I teach you how to change the value of a variable? I don't think so. Okay, so we can't use a let. Well, you can try to use a let, but it's going to be problematic. All right, so we got to do this the old school way. Go ahead.
Make a small function that just constantly runs through itself, comparing to, you take a list and a number,
No, I think you're on something.
takes in two variables, then you take one variable as the number, the next variable is the rest of the list.
Something like this. You take in the current maximum value and a list of integers.
Just compares them, and if one of them's small, whichever one's smaller, that's what you pass into the function the next time you get the code of the list.
All right, I'll keep doing these as ifs for right now. So if null, list of integers, then return cur max. Otherwise, we need to compare cur max to the car of the list. So if greater than car LOI cur max, if that's the case, if we have a new winner, then we're going to call find smallest, passing it the car of LOI and the cooter of LOI. Otherwise, we'll call, Oh, I'm finding the smallest. Thank you. Apparently, I'm not doing real great with my greater than the less than's today. Otherwise, it's find smallest, Kermax, and the cooter of LOI.
Why are you calling it Kermax?
That's the current maximum number. Oh, because I was in my mind, I was doing the greater than thing.
You're looking for the small one.
Yeah, I'm looking for smallest. We already established that I'm confused. Kermin. All right, so if the list is empty, return Kermin. Otherwise, if the first element of the current version of the list, is less than the current minimum, then we'll call find smallest, passing our new winner in along with the rest of the list. Otherwise, we'll call find smallest, keeping our existing winner, Kermin, passing it the rest of the list. All right, so this is find smallest. So if I have a, let's just do, I'm going to steal this here real quick. We'll test this. This guy's going to be called find smallest, and find smallest takes in, we're going to go ahead and pass it in 8. And the rest of the list, just to simulate how we might use this. Pass in the car along with the rest. All right, so this should, in the end, give us a 2. Should be our answer out of this. There's our 2. So now I have the ability to get the smallest value out of a list. Okay, does that help us? Well, if we're sorting, isn't getting the smallest value an important aspect? Okay. So now, once I have the smallest value, I want to keep that, right? So I'm going to be building a new list. My sorted list is going to have the very smallest value being the first element of my new list. But I also need to do what then? I need to get it out of the original one. Okay? How do I do that? Let me change this up a little bit. Right now I have find smallest that gives me the smallest element. What if I want to now find the first index of that element in the list? Because I need to know where it lives. Huh?
We have list ref, but
We have list ref, which gives me the element at an index. I need the other way around. I need the index of an element. Oh, you mean did we already write it?
Yeah.
Yeah, we might have, but we're just going to write it again real quick. All right, so we're going to give ourselves another little helper. All right, so I know what the smallest value is now in a list. Now I need to find out where that value lives. So I'm going to say define find first index. And this guy is going to take a lambda, going to be a lambda that takes in a value and a, well here, let's have it take in a number and a list of integers, those two things. And it's going to find the position of that, of the number in list of elements. First position of it. All right, so if null list of integers boil down to 0. Probably doing a math problem here, right? Else, I need to find out if I'm currently looking at my match. Okay, if I'm currently looking at my match, that is if EQ, num, and car of LOI, if that's the case, also return 0. If it's not the case, what am I going to return? Plus 1 and find first index, passing it num and the cooter of LOI.
so if you're looking at it, you're just going to return 0.
Well, the 0 will be, if it's the very first thing in the list, If I have a list of one thing and I'm looking at it, it'll return a 0. Otherwise, if it's the next element, I'll return 1 plus 0, which will be 1, the bucket in there. So here, let me show you this. So
Wouldn't you return num? Because if you're going
num's what I'm looking for. I want the position of what I'm looking for. So let me throw this 8 back in here.
Okay. Okay.
And now what I'm going to do is I'm going to say find first index. And we'll say find first index of 8. This should give me a 0. Then I'm going to say find first index of 2. This should give me a 1. Find first index of 5. This should give me a 2. Find first index of 3. Okay? And now finally, find first index of, let's say, 7 is going to give us a 5 because we ran out of stuff. And notice we hit here. But really, I could say like subtract 1,000,000 or something like that, so it comes up with some negative number, right? But because of how we're going to be using this function, we're using it assuming we found the smallest value. Now where does that value live? We're always going to be calling this function with the full knowledge that we'll find it. Go ahead.
So the function is returning the number that's being added up, like in your last else, the else portion of your last statement. So you're returning the sum of 1, and then
Yeah, ultimately this is the index of function from the string class. Okay, so each time if I found the value I'm looking for, go ahead and boil down to 0 because that 0 is going to be the result here.
and once the function's finished, it's returning that number.
The sum of all these numbers together. Every single time I take a step forward, I add 1. Okay, it's not at bucket 0, it's at bucket 1. It's not at bucket 1, it's at bucket 2. It's not at bucket 2, it's at bucket 3.
it'll hit 0, and then as it's backing up through the amount of recursion you did.
Yeah, it won't add an extra number because you found it. Make sense? All right, so now we have a couple of tools. We can find the smallest value. We can also find the first index of the smallest value, of a value. Okay, of a value. All right, so now I have a couple of tools available to me. All right, how do I remove a value at an index? Notice we're solving little tiny problems, right? Break problems down into their smallest parts. So now let's say I want a function that removes an element at an individual index. So define remove at index to be a lambda that takes in a pause and a list of items. And I want to return a new list that's the old list with position pause, 0 indexed based position pause, not there. So I want everything from bucket 0 up to but not including pause, and everything from pause plus 1 to the end. How do I do that?
So if pause is 0, you're just going to skip that bucket.
Yeah, pause is 0, return the cooter.
Yes.
Here, I'll show you another predicate here. 0 pause. That guy exists. Otherwise, you could just use the equal sign to find out if pause is equal to 0. Okay, so if pause is 0, then return the cooter LOI.
Yes.
Everything but the first element. Okay. Now again, we don't need to do error checking on these because we know that things that we're removing exist, right? So we're kind of keeping that in mind. I see a lot of smiles in this row. What are we doing in the middle there? We have videos up. We have games.
You guys looking at porn?
That would be a very interesting developing story at Concordia. Yes.
Do remember that there's a camera behind you.
Directly behind. All right. So if pause is equal to 0, return the cooter of LOI. Otherwise, what if pos is not equal to 0? That means pos is something else.
You're going to call remove at index again.
Well,
Well, you're going to cons.
we're keeping the current guy, right? So we're consing the car of LOI
Yeah.
onto whatever's returned, whatever is returned by remove at index, passing it. Pos minus 1 and the cooter of LOI. Right? What happens when we finally hit our position?
Well, then pause and be 0.
Turns the cooter. But we're going to be consing a list on.
The cooter is a list.
You do amend.
Ah,
Amend the cooter to the
good.
list.
Today's theme is cons versus append. Cons requires a list as a second element. The cooter of the list is a list. So we don't need to worry about the empty list, and we certainly don't want to do an append here, right? We actually, append would be an error. We get an error with append. All right, so this will remove at an index, ultimately giving us a new list with the thing removed. So if I say remove at index, and let's say I want to remove at bucket 2. This is 0, this is 1, this is 2. So I should get the list 8223 as a result here. 8223. Okay? So there's my remove at index. Let's just make sure it also works for the first element. 2523. And this is 0, 1, 2, 3, 4. So let's make sure it works for the fourth element. 8252. Okay? So it works for all elements that are real elements, right? We don't need to do error checking beyond that. All right, so now I have the ability to find the smallest value in general, to get the index of that value, to remove that value. Do we have all the tools we need now to write sort 2 or sort KK thanks? Define sort KK thanks. So thanks like that?
Yeah.
Is a lambda that takes in a list of integers. And what we're going to do is we're going to ask if it's the empty list. If it is, we'll return the empty list. Otherwise, what are we going to do? Well, the first thing we need to do is we need to find the smallest value, right? So we'll say, what do I call it? Find smallest. Yep. Find smallest, passing it the car of LOI and the cooter of LOI. That's going to give me, this is going to boil down to the smallest value in there. Make sense?
Didn't find smallest just pass?
I think we have two. We have a cur-min,
Oh.
cur-min and LOI.
Oh yeah.
Okay. Now, I want you guys to be on the lookout right now for why a let is a good fit right here. Okay? We're not going to use it yet. All right, so find smallest. This guy right here will boil down to what? The smallest value in LOI. Okay, so we have the smallest value in LOI right there. Now I need to get the index of that smallest value in LOI. So that's find, what do they call it, first index? Find first index. Of that value in LOI. So now this will boil down to the position in LOI of the smallest value. I no longer have the smallest value though. Didn't store it in a variable. So if I want to get that again, I'm going to have to call the function again. Not the end of the world, but just reason why we need variables, right? Okay, so now I have the position of the first element, the position of the smallest element in the list. Now I need to remove the element at that position from our list. So I'm going to call remove at index. And what am I removing? I'm removing bucket pause, which is this guy right here. Here, let me just kick this down a line. So I'm removing bucket pause from the current version of LOI. So this guy is going to ultimately boil down to a new list with the smallest element removed. And what do I want to do with that new list? Well, I want to cons find smallest onto calling sort KK thanks on the new list with the smallest element removed. Make sense? So now, well, let's see, where's my, why isn't this one? There we go. And we called this sort KK thanks and new quote. There's our list 22358. Make sense? All right, now, obviously that was a lot of work. I suspect a few of you probably came up with more,
More better.
not more better yet.
A lot worse.
Okay, more compact solutions. Fair enough? But for the average student in this room, was any individual part of what we just solved horrifically over your head? Well, besides you, you probably need to drop. Okay, so if I had just told you to write a function called find smallest that returns the smallest value in a list, that wouldn't be that big of a deal, right? That's a doable function for you to write. Similarly, if I said find first index of an element in a list, that would also be something we should all be able to write. If I asked you to do remove at index, that should be something we all can write. And after we did that, then putting them all together. So we have these three power tools that we've just purchased from Home Depot, and now we just have to use them together to pull this off. All right? Now, how would I modify this so that I'm not actually calling find smallest two separate times? That's where my let comes in. So as a programmer, when do we store something in a variable? When we need to use it more than once. In this case, I need the smallest value here, and I actually need it again right here. So I need that value twice. Therefore, I need to go ahead and create a let environment so that I can hold on to that value. So right here, what I'm going to do is we're going to create a let. I did introduce lets, right? Okay, so we're going to create a let, and we're going to call this guy the smallest. And the smallest is going to be equal, oh, not that guy. The smallest is going to be equal to whatever's returned by that. Now, I no longer have to say this. I can say the smallest. And I no longer have to say this. So I want to make sure I get it right. Now it's the smallest. So I store the variable once, use it two different times down here. Ruh-roh. Let's see. Oh, hold on. I think I've broken this. Curly brace diarrhea. is our list 22358. Makes sense? The use of a let to give us a local environment to store a variable. I mean, the other way wasn't necessarily incorrect. It was just, I mean, I'm not saying this is super efficient, but it was even less efficient before. Go ahead.
So when you use a let, do you have a quote? So you have opening parenthesis and the word let, and then you have the definition variable. Does the closing parenthesis happen right after that line, or would you wait until you've executed the block of code?
The first part of a let is a list of variable definitions. So right here I have a list of two lists so that's this guy right here. So this particular let environment only defines one variable called the smallest. So this is the to list. So that's the first element of the to list. This is the second element of that to list. And there's only one to list in this let. So we can certainly have a second one in here if we wanted and say A is 5, for example.
So then you close the let condition after.
The let is at the very end because this stuff right here is the body of that let. It's the stuff that's within the scope created by that let. All right, questions on that one? Makes sense how I approach the sort? All right, what was the next one? Sort predicate. Is this our last one?
Yep.
Oh, so really this is just the one we just wrote, with the exception of instead of just calling sort outright, we pass it a predicate and we don't necessarily call find smallest. We call find the one that meets that predicate. So we just modify this guy to take in a third element, a predicate, pass it there, replace that predicate right here. And then the rest of it should kind of just work. Yeah, it shouldn't be a big deal for this one, now that we wrote all that. So the important thing I want you to get out of this is how we went about solving this last problem. So easily this last one was the hardest question of all of them, right? But it became a lot easier when we broke it down into tiny little steps. I've been saying that since you were freshmen, okay? That we need to break our problems down to little baby steps. We showed it in our book here, like the first or second day of class, whatever it was, where the book specifically says, break problems down into their individual little parts. Right? Don't try to solve the complex, hard problems just thrown in front of you. Solve the little baby problems that you can then put together to solve the harder problem. That's how our CPUs work. Our CPUs have a whole bunch of really simple solutions written in them, those magic tricks. And we wire them together in a certain order, and in the end, we actually have solved a problem. Make sense? Questions, comments, concerns, bribes? All right, next assignment is up. I think I've only given you, 3 questions? Okay, so that one should only take maybe 8 to 10 hours. I'll see everybody on Thursday.